Hello, happy Monday. New week, new hypothesis test, and new episode of Stats with Mats. Today we're going to be continuing Wednesday's material. Last time I showed you the equation for expressing any line, any bivariate relationship displayed as a scatter plot. And today we're going to actually go about calculating the unknowns of that equation by hand. So we'll work through the formula. Well, first I'll start with review of the components of the line, just to make sure we all have the correct understanding of what a line is and how that stands in for interval level data. Then we will calculate both A and B from the equation y equals bx plus a. Simple enough. Before I get started, I just want to point out that today, as I'm filming this on a Saturday, actually, from my panic room, and all day today, Big Ten Network has been airing rivalry-themed programming, Ohio State and Michigan. So if you're watching Big Ten Network today, I will just point out that you are watching multiple, many different instances of Ohio State's biggest wins over Michigan, and they're also including several airings of Michigan's one victory over the last 16 years. Just, not trying to criticize anything. It's just what I'm seeing on my television. Okay, so let's get into regression by hand. Here's today's agenda. I already told you today's agenda. I'm sorry. It's too late to start over. So anyway, let's start with review. Here's what the regression equation looks like. Y equals bx plus a plus e. If you're wondering why I keep putting bx first when the graphic here is a plus bx plus e, since this is additive, it doesn't really matter what order you put these in. Either would be accurate. You can do a plus bx or bx plus a. I am personally, just out of habit, fond of expressing it as bx plus a. And within that equation, let's run through the 5 letters and what they mean. Y refers to the value of the dependent variable. That's the thing you are trying to predict using additional information. What is that additional information? That's X, the value of the independent variable. I cannot stress this enough. X and Y always refer respectively to the dependent and independent variable. Y is the thing that you're trying to predict. X is the thing you are using to predict values of Y. It's not wrong to switch them around, but that would, of course, shift your hypotheses, because hypotheses here are always going to be expressed as given a 1 unit increase in X, assuming an increase in X. So if you switch which variable is X and which variable is Y, you are now implying a different type of relationship. Now, X and Y, jumping down to the bottom of the slide just a little bit, X and Y refer to given observed data. You will not have to ever calculate X and Y. Those are given to you. Something has to be given to you in order to do some type of hypothesis test. What you're really trying to calculate here is A and B. And actually, I should say B and A, because it must be done in order of B and A. That will become very clear once I show you what the formula is. All right. B refers to the slope coefficient. B refers to what is the magnitude of the change in Y, assuming a 1 unit change in X. So that's what you're ultimately trying to calculate for interpretation purposes. Now, A represents the y-intercept. Like, statistically, we would call A the y-intercept. I think intuitively, we can understand A to be the value of X when Y, or excuse me, the value of Y, the value of Y when X is set to equal 0. And that's a baseline. Remember, we're expressing everything here given and assuming a 1 unit increase in X. So a 1 unit increase from what exactly? Well, 0 acts as the baseline for the equation. And then E is the error term. The error term is necessary for individual data points, but it is not actually necessary for the entire regression equation. But I'll get to that in just a few slides. So really what I'm holding you responsible for and what I'm expecting you to practice on this homework coming up on Friday is how to use paired data at the interval level of measurement to calculate both B and A, the slope coefficient and the y-intercept, respectively. So before we get started doing that equation, let's run through what this might look like in an actual data set. And I should say data set, very carefully, because the first example I want to show you only has 2 pairs of data. Okay, so practicing our interpretation here, we know y equals bx plus a. In such a situation, we can use just this very simple example here to practice our interpretation of B and our interpretation of A. So within this example, I have 2 situations. X is going to refer to the number of patrol cars deployed on the freeway. Let's say I-94, I guess. And Y refers to the average speed of drivers on that freeway. Now, when X equals 2, that is to say, when I have 2 patrol cars deployed on the freeway, the average speed of drivers is 75 miles per hour. What happens when I load up the freeway with a whole bunch of patrol cars? Okay, well, when X equals 10, and that is given data to you, then the average speed on the freeway equals 35. So all I have is 2 data points here, and that's not really enough to calculate a regression, but we can use it to practice our interpretation in a way that I hope will be very intuitive. So when X equals 2, Y equals 75. When X equals 10, Y is going to equal 35. So given an increase in X, what's happening to Y? It appears that Y, the average speed, is decreasing. So that tells me right there that my value for B should probably be negative. Okay, so that's the situation. I have a relationship between number of patrol cars and average driver speed on the freeway, X and Y respectively. 2 data points, that's it. If you want, knowing what you have here, you can actually calculate, it's actually not that difficult to calculate B and A already. You can do that because it's simple algebra at this point, but I'm not going to require that of you. I want you to interpret at this point. So if I fit the regression line, that is to say, if I calculate the unknowns here, A and B, here's what you're going to get. And feel free to pause it if you want to try the algebra here. But if you want me to just tell you what the answer is, Y equals negative 5x plus 85. No more unknowns, because keep in mind, X and Y can take on specific values depending on the fitted data points. 85 is the value of A, and negative 5 is the value of B. Now, what is that telling us from a social perspective? Let's practice. If B equals negative 5, and A equals 85, I would like you to write down a practice interpretation for B, for the slope coefficient. Okay, feel free to pause it if you need more time. Here's how I'm interpreting that. A 1 unit increase in patrol cars is associated with a 5 mile per hour decrease in average speed on the freeway. I have to reference the units of my variables, and I have to reference that the relationship is negative. As X is increasing, Y is decreasing. And that's pretty easy to just eyeball as well. When I have 2 patrol cars out, people are driving 75 miles per hour, but when I got 10, people are only driving 35 miles per hour. You can easily eyeball that and see the pattern. But the specific unit of decrease is 5 miles per hour per additional cop car on I-94. So I'll repeat that one more time. A 1 unit increase in patrol cars is associated with a 5 mile per hour decrease in average speed on the freeway. All right. One other thing we're going to want to talk about here, that y-intercept. Notice this is negative 5x plus 85. So let's interpret the y-intercept. You will remember the y-intercept is the value of y when x is set to 0. So you're essentially asking yourself, like, what would people be driving if there were no patrol cars deployed on the freeway? You can actually kind of figure this out by simply looking at the value of y when x is equal to 2. Even if I didn't tell you what this equation was here, you know that each additional car you add drops the average speed by 5 miles per hour. So if I, in theory, go from 2 cars to 1 and from 1 to 0, what's going to happen here? Well, for each car I remove, the average speed will increase by 5 miles per hour. So if when x equals 2, y equals 75, it makes a lot of intuitive sense to me that when x equals 0, I'm just using that same average change in y given movement in the independent variable. So please write down an interpretation for the y-intercept and pause it if you need time to think that over. When x equals 0, the average speed on the freeway is 85 miles per hour. That's a perfectly accurate interpretation of what the y-intercept is telling you here. So the last time we talked about this, I was mostly focused on helping you understand the components of the equation. Now what I need you to grasp is how to grab those values once they are fitted, once they are calculated is what I mean by that, and how you can draw some interpretations about a real social situation right then and there. Okay? All right, so moving on. Where's the error term here? Notice how every time I show you the algebra equation, it's y equals bx plus a plus e. And every time I show you an actual trend line, a data line, it's y equals bx plus a. So what happened to e? If you already know where this is going, then you're in pretty good shape. If not, that is absolutely no problem at all. You just need to think this through. The error term is almost never shown for the lines equation. And that is because the error term is calculated using the sum of squares property, okay? Pardon me, it's the error term is calculated by balancing the errors above the line and below the line. And so I've said that the error term needs to be the smallest it could possibly be. Well, in this case, the error term is going to be calculated for a specific value of x. We will have a value for e when x equals 2. So when x equals 2, the average speed is 75, right? And when x equals 10, the average speed is 35. So neither of those will be the mean average speed. The average mean here is going to be like 55 or 60, whatever it ends up being. And so knowing that, 55 actually is what it would be, I will get a value of e, an error term, that is different because it's referencing each value of x. But if I add all my error terms together, which is what you're doing for the average regression relationship in y equals negative 5x plus 85, my errors that are positive and my errors that are negative will cancel each other out. It's no different than when you did deviation and summed them up to 0 to make sure you hadn't made a mistake yet, okay? So on average, e's will cancel out to 0. You can calculate an error term for each value of x, but you do not actually have to do that for all values of x because that would just sum out to 0. All right, so hopefully everybody's regaining their familiarity with the regression line. So using this equation, we can actually infer values of y. So y equals negative 5x plus 85. I only have 2 data points here, 2 and 10. But regression is so powerful because it allows us now, what if I wanted to know what's the average speed when x equals 5? Okay, well, I have a higher value than that, and I have a lower value than that. Now it's just simple algebra. Well, y equals negative 5 times 5 plus 85. Do you see how that's operating there? I kept the value of b, and I kept the value of a in there. And now I'm going to try and figure out the value of y when I have 5 cop cars deployed. I just plug that in as a potential value of x. So negative 5 times 5 is negative 25. Add that to 85, and y equals 60. Put another way, when x equals 5, the average speed on the freeway is 60 miles per hour. And I can do that with any value for x that makes sense to me to try and infer the values of y. All right. So, reviewing my interpretation, a 1 unit increase in the independent variable is associated with a b unit change in the dependent variable. This is by far the most powerful technique we have learned thus far. I hope you can see that, like just how powerful this is to be able to predict not just strength of relationship, but the magnitude of the effect. And that is why this is by far the most important method in a sociologist toolkit. And also, with every other hypothesis test I gave you, I was stressing that this can only be used for specific combinations of variables. So a t-test, we needed 2 means and only 2 means. For ANOVA, we needed an interval level dependent variable and an independent categorical variable. And for chi-square, we had to have 2 categorical variables. What regression will do, which is just so useful, 1, we can go multivariate with it. And 2, we can alter just algebraically, we can work through and alter the equation so that it can accommodate any type of variable we want. Any type of variable we want. And I'll get to that at a later point. But for now, know that we are studying OLS, or ordinary least squares regression. There's all sorts of other regression models that are designed to predict different types of outcome variables. We can do this with, we can have what are known as logistic regressions, Poisson regression, zero inflated models, negative binomial models, Cox models, multi-level models, just to name a few. There's dozens and dozens of regression models out there. But this is the first one. This is the one that is the baseline for everything else, and that's why we're sticking with this today. Okay, so here's the million-dollar question. Can we do this by hand? Can we use our 5 fingers and our brains, our powerful little brains, to predict values of y given the units of x, and use that to establish the slope coefficient of a line and the y-intercept according to that slope coefficient? Of course we can, but realistically, we can only do this using 2 variables. So I have some good news for you. We're going to do this by hand today, and then this is the last hypothesis test that I expect you to know how to do by hand, the very last one. It honestly brings a tear to my eye to know this is the last time we're going to be doing math by hand. But fret not, or I should say I will fret not, because I know that there will be many other opportunities to do just interpretation, even if we didn't do the hand calculation. So yeah, this is the last calculation required of you by hand, and the formula is actually going to look very familiar. I hope you've been able to ascertain and pick up that bivariate regression is very similar. In this case, it is very similar to bivariate correlation. And as a result, the formula is going to look somewhat similar, and the process is going to feel very similar to us. So this is good. I was very pleased, and I mean very pleased, with how people did on the homework and handled the process of the math for Pearson's correlation coefficient. That's good. You don't want to mix up the formulas here, but you do want to use the experience that you got calculating Pearson's R and apply that to the summations of X, Y, and all sorts of other stuff in order to get our hands dirty with this. So what we're doing here, it's just a variation of the bivariate correlation equation, but we're going to need a different equation to account for the fact that we're trying to do something a little different here. We want not just, we want the magnitude of the effect, not just the strength of the relationship. All right, you ready to get your hands dirty? Let's do it. You're going to need two formulas here. You will need an equation to estimate B and another equation to estimate A. Here's my instructions. Calculate B first. And that's not just advice, that's actually instructions. Because look at the equation for A. You will see that the equation for the y-intercept makes use of what you already got calculating B. So you have to do the top thing first in order to be able to have all the components you need for calculating A. So again, step one, don't panic. Let's just go through the components here. B is defined as n times the summation of xy minus the summation of x times the summation of y over n times the summation of x squared minus the summation of x, pregnant pause, squared. And once we do that, then B gets inserted into the bottom equation. So for A equals the summation of y minus B times the summation of x over n, where n references the sample size, which is pairs of data. So in that cop cars and average speed example, we had two pairs of data, 4 numbers, but only 2 pairs of data. So I'm just scanning and glancing at the formula here, and I see I'm going to need the summation of x, the summation of y, the summation of xy, and the summation of x squared. I hope this is starting to sound familiar and to jog some of your memories from what you had to do last week. So if I need the summation of x, y, xy, and x squared, perhaps something like this is going to help us. Does this look familiar? I hope so, because it is the same pairs of data from last week's example. I promise this isn't just me getting lazy and not doing a new example. I have to do a new example for your homework. No, this is me. I want you to see how the same kind of calculations get used in a different way to produce a slope coefficient here. Okay, so you will remember here, x and y both refer to interval level variables. When x equals 5, y also equals 5. When x equals 10, y equals 20. When x equals 6, y equals 4. When x equals 8, y equals 15, and so on down the line. So what is my sample size here? It's 12, the same 12 data pairs that I worked with last time. And so what I want to do is use this formula to calculate, or not the formula, just use this table to first calculate. The first thing I would do is add up all values of x. That's the summation of x. Then I will add up all values of y, and that's the summation of y. Then I will take each x, multiply it by its corresponding y value, and then sum that, all 12. And then finally, I will take each value of x, square it, and then sum all 12 answers for x squared. So when we're done with this table, what you should have is x, the summation of x, the summation of y, the summation of xy, and the summation of x squared. We're going to go through the steps of the hypothesis test here. But for now, since it's up here and you can just look right here at this data table, why don't you try your hand at finishing out this table? All right, pause the video if you need more time to get the summation of x, the summation of y, the summation of xy, and the summation of x squared. Put that aside, and we're going to come back to it. Step one, what do we know? This is exactly the same as for the product movement coefficient for bivariate correlation. We know x is a dependent variable, y is a dependent variable, and we have 12 pairs of x and y. That's it. I just have to list my variables. No means, nothing of the sort, just list those out. Step two, hypotheses. Even though regression is always interpreted assuming an increase in x, a 1 unit increase in x, you have to know if you've been specifically instructed to assume a positive, negative, or negative relationship. Now, in this case, you were just asked, is there a relationship between x and y? So here's how I'm going to set up my hypotheses. On the null side, there is no effect of x on y. H1, there is an effect of x on y. Another way that you could express that is I could write for my null hypothesis, as values of x increase, values of y are not significantly changed. Because I could observe a significant relationship that is positive, and I could observe a significant relationship that is negative. So if I just want to know how these two things are connected, then another way to express the alternate hypothesis is that H1 is as values of x increase, values of y will either significantly increase or significantly decrease. If you're going to write it like that, you're going to want to mention the word significantly. That's important. And now, here's my Easter present to you. In terms of step 3 and 4, you don't actually have to do any of it. But I'll tell you why. I want you to understand why you're not required to do it. It's not that this is skipped. It's not that this is unimportant. It's because if you calculate significance by hand, that's a wildly, wildly complicated process. And the computer can do it for us very easily. When we interpret multivariate findings, I'll want you to know how to figure out from the regression output whether something is a significant or a non-significant finding, or put another way, whether you would reject or fail to reject the null hypothesis. In terms of doing it by hand, I don't require it because it's ridiculous. It's just, it's out of control. So steps 3 and 4 here, if you really wanted to do it, you would have to set your alpha level, which is easy enough, but then you would need to divide the estimate of B. You'd first have to have that, divide that by its standard error, and then you would do a t-test between B and 0. I'm not going to actually ask you to do that. So just for now, please take it for my word that this still happens. But I just want you, when you're doing it by hand, all I care about is that you get the right answer for B, the right answer for A, and can interpret it in a full sentence accurately and appropriately. Okay. So getting to work here, I asked you to fill out this table and to get the summations. Pause the video and do this if you haven't already. What you should have gotten is the following. The summation of x is 74. The summation of y is 134. The summation of xy is 942. The summation of x squared is 536. And how many pairs was I working with? I was working with 12. Okay. Assuming you have these answers here, let's move on and calculate B and A. B first. So using what we just calculated, again, the summation of x is 74, summation of y is 134, summation of x is 942, summation of x squared is 536, and n is 12. So let's plug this in. N equals 12. The summation of xy is 942. The summation of x is 74. The summation of y is 134. That's what I need to establish the parameters of my numerator here. So 12 times 942 minus 74 times 134. Word of advice here, I encourage you to do this one term at a time. If you try to plug this all into your calculator, there's a lot riding on you getting it right. There's a lot riding on you expressing it with your parentheses and the way you type it out in a way that the order of operations will be followed correctly. So I would suggest doing this one step at a time. Then the denominator here is expressed as 12 times 536, that's the summation of x squared, minus the summation of x squared. So I had to take 74 and square it as the last part, bottom right part of the equation here. All right, I would like you to solve that. All right, what do we got here? What you see here is the same. I actually haven't pushed this forward yet. That's the same equation that was on the previous slide. This division equation for B will reduce to 11,304 minus 9,916 divided by 6,432 minus 5,476. That will reduce to 1,388 divided by 956, which will then reduce to 1.452. Remember, that's the slope coefficient. It's positive, so I know there's a positive relationship here, which should not surprise you. When you calculated Pearson's correlation coefficient last time, you would have seen a positive value for R. So if R is positive, then B here has to also be positive. So how should you interpret that? Please write it down in a full sentence. And if you're ready, I'll tell you my interpretation. A 1 unit increase in X is associated with a 1.452 unit increase in Y. Why is it an increase? Because the coefficient is positive. If it were negative, we'd have to interpret this as a decrease, but we don't because it's positive. Not too bad, right? Right? I hope. God, it's so sad doing this without any feedback. What can you do? But there's one more step that we must complete. One more. You will remember that B was a component of the equation that would allow us to calculate Y, or A, pardon me. A, oh God, A, the y-intercept is what I was talking about there. So going back to our table, same parameters, but I'm going to use A as my outcome here. And A is equal to the summation of Y minus B times the summation of X over the sample size. So this should be expressed as 134 minus 1.452 times 74 over 12. Try your hand at solving that, please. And if you're ready to see the answer, I will move on. 134 minus 1.452 times 74 over 12 reduces to 26.55 over 12, pardon me. And that reduces to A equals 2.216. What's my interpretation there? Let's include B here to make it complete. A 1 unit increase in X is associated with a 1.452 unit increase in Y. And when X equals 0, Y equals 2.216. That's correct. And that's beautiful. Now, as far as where we go from here, one of the things I keep teasing and previewing is that we can go multivariate with this. And that is not something that can realistically be done by hand. So as a result, we're going to be looking at stata output and would have been doing stata output if this whole thing hadn't happened. So what I did is I put these two variables into stata. I made var1 X and I made var2 Y. It's just a couple things I want to point your attention to here. I ran a regression. We are going to go through interpreting this output at length in the next video I upload. But what do you remember? What was our slope coefficient, our value of B? It was 1.452. 1.451883. That rounds off to 1.452, right? And then what is my y-intercept? Let me go back. What was it? 2.216. And what do I have here? See where I say underscore CONS? That's the constant of the equation. Stata has calculated that as 2.213389, which I would round off to 2.213, I guess. Yeah, 2 point. So we're very slightly off. But look at how Stata has calculated it. Where I rounded, they didn't, and so as a result, or they rounded a much deeper part of the equation. So but I think you see that these are pretty much the same thing. That's what we're going to be operating with. All right. I hope so. Hopefully that made sense. Hopefully you feel good about this. The homework for Friday is something you can get started on immediately. Something you can get started on right away. We'll only reference calculating bivariate correlation by hand. Okay. A future assignment will deal with multivariate regression. Oh, and I forgot, I actually did have a movie thing to say. I'll make this quick since the video is wrapping up. But I watched The Prestige somewhat recently, and I was watching Hugh Jackman walk around in his 19th century top hat and cane. And I was asking myself, at what point is it acceptable, like at what age is it acceptable to walk around with a cane where you have like no physical disability? So like if you see an elderly man walking with a cane or something, it's like he doesn't have to be disabled. He's just like old and is allowed to use the cane. I was curious about this. So if you want, email me your number for when it's acceptable to walk around with a cane if you don't really need a cane. Because Hugh Jackman in The Prestige definitely did not need that cane. Anyway, let's keep it up. We are 2 weeks out, from finishing. Like I said, keep working for me and I will take care of you if and when you need to be taken care of, okay? Yeah, and that's it. Have a great rest of your day. I'll be back in touch with you on Wednesday. Bye-bye.